here for many reasons. But it's great to have Philippe here. He's an associate professor at the ETH University in Zurich. He's directing the Block Research Group. It's an amazing group of not only researching, but also building and applying what they are researching. They are experts on computational design, form finding, computational form finding, and their expertise is actually taking the Catalan vaults, not only the Catalan vaults, but for the ones that you have been in Venice, you have probably seen this kind of amazing cell vault structure out of bricks. He's working a lot with unreinforced, let's say, vault structures, but also curved cells and concrete thin cells that he will be showing to us today. As an expert of fabrication, what it is important, I think, and what he can bring as a knowledge today is how we can connect the research with the industry and the application, but also how can fabrication in combination with material performance and computational design can allow us to build things that until now we thought it was impossible or we thought it was unsustainable. So no more to add for Philippe, just to thank you very much for being here today, and please help me welcome him.
All right, thanks a lot for this very nice introduction, Areti. Is it okay, or should I hold it closer? Yeah, I hope it's okay. All right, let's go. So I'm very excited to be here. Thank you. Finally, I get invited here, so that's good. Talking about today is basically our research and some of our projects, but particularly what I want to share with you is basically that it's not only my passion or what I strongly believe in, but it's also how we tend to discover new things, going back to the past. And so that is why perhaps my title should not be called Novel Shell Structures, because there is not much we can invent anymore, but we can certainly still rediscover things in the past. And I hope that you will be as passionate about this rediscovery of why master builders could do what they did in the past. So for this, I'll first start where it started for me. I did my PhD at MIT in the assessment of historic structures in masonry, vaulted structures in brick, in stone, and so on. But then you will see that actually what passioned me was the discovery to the tools that we developed to explain the stability of these historic structures. You can actually discover new ways to generate exciting form. And then I'll show you a lot of examples why I care about this. And I hope through these examples you will see that there is a value to learn about where cathedrals are still standing. And then all the way at the end, most of the talk will be about unreinforced masonry, but I will show you that it's worth to look back at the Gothic cathedrals to actually discover absolutely new ways to do things in materials, in systems that are not just masonry. Right, so let's start at the beginning. So this is where it started for me, this nice adventure. These are the beautiful fan vaults at King's College at the University of Cambridge. My advisor, John Ochsendorf, studied there. And these are actually still a little bit a challenge to explain, or in practice to really be sure why they're standing, how long they still will be standing. And if I throw a few numbers at you, then you might understand why. These span about 13 meters. And the structural depth is only 10 centimeters in the middle and 15 centimeters at the end. So they're large pieces of stone. They're kept together just by geometry because they have been standing for more than 500 years. So there's no steel, there is no reinforcement, nothing else than geometry keeping them together. So this is a very hard problem, actually. And to put these numbers a little bit in perspective, these structures are proportionally, if you, for example, take the length of an eggshell, they're literally as thin as an eggshell. So just to sketch a little bit the audacity of the master builders, this is centuries before the current theory of structures that we use. So they were basically able to design this. Where did that come from? How did they discover these forms? What worked? Of course, you know this very simple and first very powerful, nonetheless, way to discover a structural form. The relation between something that hangs in pure tension, and if you freeze this geometry and you flip it over, then it stands in pure compression. I don't have to talk about this here, because of course we know one of the most famous examples is Gaudi for the crypt of the Colonia Güell. He basically used these kind of inverted principles. But basically, if you look a little bit closer, what's going on is that if you don't care about material properties, so you design a beam to fail at a certain point. So what we typically do in modern structures, interested in a good geometry, in basically something that needs to be stable, then you have a very interesting situation that stresses are absolutely irrelevant. That basically it's really the geometry that is important to be controlled. And that is why these Gothic master builders could build just by using proportional rules or by using physical models. So they actually used models to understand what worked at a certain scale, and then they scaled it up. And so this is an extremely powerful concept, because if you follow where the forces want to go in compression, stresses are so low that it actually doesn't matter at what scale you're building. And so this is something extremely powerful. This is, of course, only looking at statics. This is not looking at stability and things like that. These hanging models were very painful. You all, many of you will know that Gaudi spent almost 10 years with his team designing this crypt and so on. So that is why people started to develop these graphical methods to discover form basically on paper. And how they worked is you always had the geometry of the structure, and then this diagram visualizes, represents the equilibrium of forces. Very simply, you could just measure the length of the elements. And so all these elements, you could read the forces by measuring their length, and that gave you the magnitude of the forces in them. So in the beginning of my PhD, I was trying, or that was the premise, to extend things in 3D, and I found this amazing book by William Wolff. But in the back cover, I like to show this slide because you see that it was 42 years ago that anyone touched this book. So I was fairly convinced that I was doing something absolutely obsolete. I got a job at ETH, which is not a bad place to be. So perhaps this finding of this book was actually a nice starting point. All right, so that's where I come from. That is also what we do professionally with ODB. ODB doesn't stand for Old Dirty Bastards, but for Ochsendorf DeJon Block. And professionally, we mainly do assessment of historic structures. Why I say that, or why I start there, is because assessment of these very complex geometries is much harder than design. Design is a forward process. You can build in some iterations and so on, but it's up to the designer to argue where you're going for. A historic structure that is so thin and that stands for hundreds of years, to find compression states within is a very tough task. And by actually starting from that point, by actually trying to say if a structure is safe and put your signature under that it will still stand for hundreds of years, that basically pushed our tools. But so now I will maybe talk about when you do it inverse, now suddenly we have very exciting and powerful methods to discover structural form. Let's, for example, look at this extremely boring starting point. You have a circular support and you want to span spacing compression. I will talk about later why that is relevant. Let's say now that you want to build a Catalan vault. So you need to have a compression shell. So you can imagine a dome, a cupola, a dome with an opening. Let's be a bit more exciting, a dome with multiple openings and side openings. Well, in fact, all these solutions, and there is an infinite number of solutions, are basically possible for the design load self-weight. So these could also be built in compression. So you see that we have a butt can be built, or an alien, a Swiss cheese. All these different solutions are basically possible in compression only. But what's the difference between all of those? And so for this, to discover these forms and actually understand what you're doing, we developed a tool that is called RhinoVault, where we allow the designer to lay out the geometry of the forces, the projection of the forces in plan, And then this is the equilibrium of forces. And so we force the designer to basically, while designing, being always aware of the relation between geometry on the right. So for example, what is then interesting perhaps, so it's different than most of the tools that we have. Almost everything is black box. You just hit the button and something spits out. So here you need to play with these two geometries that represent different things. For example, locally attracting forces. Hopefully you know intuitively what that means. If you have a very shallow structure, then that structure is thrusting much more along that line. And so you see that you locally have a crease, you have basically a force attraction, and that allows you to start to shape structures. Develop this because you see that we can, in plan, control, for example, openings that are square, or we can control where arches need to lie, and things like that. The process is a little bit more tedious, so this tool is extremely frustrating and painful for the first half hour, but you keep using it, and 16,000 people keep using it because they basically learn something during design. And I find this something extremely important in this digital age, that tools should actually educate the designer, and you should learn something new. So here, by changing the boundary conditions, we get something that is inspired by Stuttgart 21. Maybe you know Stuttgart 21. It's more kind of a steel structure with a concrete cladding. Perhaps I should have used Rhino Vault to design it, but anyway. Let's go back where we started. So how can we compare or discover these forms? So I will show you a set of examples. Here you always see the layout of forces, the force equilibrium, and then the three-dimensional shape that results. And just by strategically choosing your force topology and redistribution of forces, you get this wide variety of shapes. And so this to me is exciting, that it allows you as designer to do whatever you want, but you know at what cost. You know how much additional material you will have to be using in order to get these different geometries. So then you see also that in order to get these peaks and valleys, you need to locally attract forces. And so these diagrams really become something beautiful to explore. And I think they're beautiful also by themselves. You can start to inverse the relation. This could become the structure, and this is then the force diagram, and so on and so on. So this to us is important, that we actually share what we do, but that we share it in a way that is not just an easy solution, but you discover also something in the process. So one of the reasons why we care about discovering compression form or understanding where the compressive forces want to flow is because if you have a funicular geometry, so a compression-only geometry, the stresses are indeed very low, and that means that you can use very low quality or very little material. So let me first show an example. I don't know if you know about this technique. It's called Valencian vaulting. So you're basically, no, sorry, this seems not funny here. Okay, this is Catalan vaulting. So once you have a boundary, you can, with a very lightweight, yeah, okay, good. So with a lightweight tile and a fast-setting mortar, you can build in stable sections. So this is extremely powerful because the key premise here is that you need only a minimal amount of support to build these geometries. And then this first layer that is done in a fast-setting mortar then serves as a permanent formwork to build up structural depth. John Ochsendorf did this beautiful book where he showed all these projects of the Spanish immigrant, Guastavino, that built all these structures in the US. When you're looking at this, and I don't have to tell you because it comes from here, but if you look at this, this is not decoration, this is a structure itself. Well, in this case, there is one tile added, but actually below it, it's exactly the same. And we're talking about just 15 centimeters of unreinforced masonry that, again, we are spanning multiple meters. So this is about 20 meters, but there's examples that are much larger that are built, again, without needing any support from below. So this is an amazing technique that we thought needed to be rediscovered. And at least in the US, there is an amazing appreciation of these structures. No surprise that the Guastavinos did all these sensational projects. They were indeed masters of graphic statics. So they discovered their form in exactly the same manners as what we now extended to 3D. project that, so this is where we come from, this is the traditional technique, but then the first project that I was involved with in this technique was a project by Peter Rich and John Ochsendorf. Michael Ramage did the entire construction follow-up. It was a project very remote in South Africa to the borders of Zimbabwe. It was a poverty relief program. So it was important to empower and to give new kind of skills and also give basically employment to the local people, but also to use as much local material as possible. And so naturally that meant that we ended up with compression shells. Here, this slide kind of shows what we're doing. We're basically using just local soil, compressed, without any burning, without any energy, just manpower and a little bit of cement to stabilize the tiles. So this is not new, but it was the first time that this was applied in tile vaulting. So it's using a traditional technique and just changing one thing to make it locally possible, because it capitalizes on local soil, but also on local labor and so on. So this is Michael Ramage at University of Cambridge. This is James Bellamy, our Kiwi master mason, and these were farmers and carpenters just a week before that. And so they're doing the first exercises in tile vaulting. Thousands of tiles, employed 12 people for 1 year. And there is actually a nice anecdote to this image, is that the women were carrying the tiles because the tiles were so weak. What am I talking about? We have about 25 centimeters. They were designed to only take 2 megapascal in compression. For the architects, that means peanuts. For the engineers, that means also peanuts. That's really almost no structural capacity. But if you hold the tile on one end, then it just breaks in bending. So the tiles are so weak that you cannot just hold them on one end. And that is why the women are carrying the tiles, because in the first week when the men were carrying the tiles, more than half of the tiles were broken by the time they got on site. So this just to show what it means to work with low quality materials. This is very traditional or typical process of tile vaulting. So this is their first vault that they're building. So you see that first we need of course formwork to build the supports, but then once you have the supports, you can arch, you can build in stable sections with this wide fast setting mortar. All the wood that you see is not support, it's just to guide the geometry, because we need to, with unskilled labor, make sure that we stick to this very precise geometry. So here you see this summarized again. You have the arch openings, and then this white layer is the one with the fast setting mortar, and then the rest can just be built on top. This image to me is very important and impressive. You see many things, particularly here to the right. These tiles that are too weak to hold on one end, if you place them where the forces want to go, you can indeed already support the person following up and building the other layers on the end. So this to me is very convincing. But what you also see is that you only have the efficiency, the off compression, if you tie back the supports. So these are the tension ties that basically control the end conditions. And this is very important, because otherwise it's just a curved beam, and then you cannot use these weak materials. But anyway, this was a very nice starting point for me, with very humble materials locally, being able to, oh, I forgot to say, what did I do? I did the structural assessment, so the equilibrium analysis of all these vaults, test them under different loading cases and so on. These were 18 meters, so literally dirt cheap, very exciting starting point. So one of the first projects that I did at ETH, together with Dirk Hebel, was in Ethiopia, trying to address this. This is the current low-cost housing. There's nothing low-cost about this, because in Ethiopia they don't have cement, they don't have steel, they don't have precision wood, so everything needs to be imported. So this, and then you see that how they make the scaffolding. This wood will never be reused. This is poisonous wood, eucalyptus in Ethiopia and so on. So they're just trying to build like us, but that doesn't make sense in these kind of conditions at all. So why not go back indeed to something that we knew how to do here, and which the Guastavinos brought to the US. One thing that I dare want to say is that an arch, it works with the arch, but the arch is not a good structural form. The arch is a perfect form for one specific loading case. But if you take additional point loads, then your force lines don't stay on the inside of your structure anymore. That means that you would need to take some bending. So you need to do something. So for example, you add these stiffeners so that locally your point loads can be carried in compression to the supports. And if you add your tension ties, then basically you replace the beam by a system of a very thin arch that needs to be stiffened, of course, with a tension tie, right? So that is the idea. So this we deployed then in Ethiopia with hanging chains, that the shape was not just a random curve, but it was a hanging model. We trained the local masons. And here you see then how these floors are basically entirely with local soils being stabilized. This is finished. The stair is not my design, but I'm quite happy that they paid attention. There is at least a little arch in there. And then the result is this box. It was designed as a box because it needed to look as a concrete-y kind of thing that looks modern. This was designed by an Ethiopian colleague. But what's important to point out here is that this is 90% soil. So where is the 10%? In the two ring beams that basically take the horizontal forces. Again, otherwise you cannot capitalize on this weak material. And the entire finished, we're talking about 5 by 8 meters, 2 floors. So this would house in Ethiopia 1 to 6 families. Just to put it in context, was entirely finished 3,500 euros. So if you calculate this per square meter, this is a little bit over 40 euros per square meter. So that is what we realized by basically capitalizing on the local labor available and not having to import materials and so on. Then follow up now, this is actually quite exciting that this has been picked up by Lord Foster and his foundation. And perhaps you have seen that he has shown this kind of concept or vision to develop these drone ports all over Africa. These drone ports that become centers of activities, civil centers and so on, where there is hospitals. They're even talking about fab labs and post offices and so on. And where this comes from, this concept, is because in Africa, 30% of the people in Africa live within all-season roads. But this is how an all-season road typically looks like in the... So this is not very efficient way to get around. This is a reality in Africa, right? And so that is why the EPFL, Jonathan Ledgard, started the idea of developing a system to very efficiently distribute emergency medicine and materials and so on without having to build infrastructure, without having to spend the billions to make a road network and so on. And the idea is to basically carry all these materials. Okay, so I don't have anything to do with that, but what I find interesting is that the vision or the style or the image of that infrastructure that basically goes to the future for Africa was envisioned by Lord Foster in basically a typology that hopefully looks very familiar, seeing the projects that I showed you before. So we jumped on board, and the particular challenge here was basically to develop a shell that is optimized to be very happy during most of its lifetime, and that can be built just with an extremely system kit of parts, so that we basically can embed the smartness of the geometry in a system so that you can send it without having to send all the experts every single time, but that people locally can actually build safe infrastructural elements. So this is at the Biennale project with Lord Foster. It was all the way at the end, so it's kind of like a gate to the Biennale. But important is that this is just a first iteration of a large infrastructural element that is extremely robust. It can be built locally, it is very safe, it can be maintained very easily and so on. And the vision is that this could extend. Just last week, if you're interested in this project, there's a beautiful issue in the AA that clarifies that people then Lord Foster were involved in this project. All right, but so we're talking about using local materials that are extremely cheap. And so we were invited for an exhibition in New York, a pavilion in Ideas City. How can we translate this idea of using local material that doesn't cost anything, that is basically wasted? And so I thought, well, can we not do like our little buddy Wall-E? Can we not start to compress our waste and start to build our structures like that? So again, with Dirk Hebel, we demonstrated this in a pavilion in New York. What did we take? We take this compressed Tetra Pak because it was only there for 3 days. So it was very important not to leave any waste behind. So this is already kind of a very efficient cradle-to-cradle kind of process. And, but just to give you a little bit of material properties, it has 1/10 of the compressive strength of timber, but 1/100 of its elasticity modulus, means it's almost as flexible as rubber. So this is really not a structural material. That's the only thing you have to tell me to get me on board. I said, great, let's build something structural with this. So we basically went to these factories to understand how these things are done. They're being made in big sheets, just with a little bit of heat and compression, no additional materials. Okay, in this case, we had to use grasshopper because we had only 2 months. And that was needed because all the way at the end, we finally generated everything. And the only non-recyclable material we used were these little straps. So we didn't want a system that had any mechanical or things like that. No surprise that this is an arch. We had much more ambitions in the form, but it had to be assembled in just 2 days because the site was extremely expensive. So we made actually a very lightweight arch that could be assembled very simply, came together very naturally. But then nonetheless, within all these constraints, we showed perhaps a little bit of fun. We showed the potential of using garbage. So this is orange juice. This is milk. To the other side, everything was wine boxes. So we basically played with this texture to make a pavilion that could be reused entirely and put back in the recycling loop. It was a nice site. We played a little bit with the arches, fanning open and closed. Very simple tricks to basically make perhaps a cathedral of waste for a couple of days in New York City. All right, so this is what you can do when you follow the forces. You can use materials that are absolutely not structural. So soil that is so weak that it breaks by itself, or in this case, compressed waste. But perhaps more exciting is to design actually as expressively as these Gothic masters. Very early project in 2010-11, we built in a very early version of Rhino Vault. We wanted to discover and present a shape that was never seen before. So in this case, because this was the first benchmarking of my PhD, the first test, if I wasted 4 years of my life or not. So this was very important to very carefully describe the geometry. So we did this with cardboard. Lara built this shell. It's a 2-layer, very simple, unreinforced style vault. So these are the 5 weeks of, there was a lot of rain this summer, very frustrating. And there it was. But before decentering, what's very delicate in a compression shell is the decentering, because it's not designed to have a very large asymmetric live load. So we devised this very high-tech system. This is cardboard dry, this is cardboard wet. So that seemed like a very natural way to decenter very smoothly and equally. So we put the entire structure on these spacers in plastic tubes. And after the 5 weeks, we cut them open, put a hose in, and everything nicely came down so we could safely decenter. And again, I know if any of you have built these shells, that much care is not really needed. We now know very much. But the thing is that these kind of funky geometries, I never had seen them in brick. And my reputation, I was a young professor at ETH, and my entire PhD was counting on this. So we were a little bit more careful than one should perhaps be. So here then there it was, with geometries that I thought were quite surprising, with geometries where I had all kinds of fights with my colleagues in civil engineering, that there had to be tension everywhere, which is very hard because there is no reinforcement or something to carry appreciable tension. Here the inside, and there it was. So of course, because this was a research project in the middle of ETH campus, we had a bit of an issue because we didn't have a permit to do this kind of stuff. Kids like to climb on it, roll off it, fall off it, and so on. This was getting increasingly an issue, so we had to tear it down. So as amateur master builders, we did a nice load test. This is 3.5 tons of sandbags. Absolutely nothing happened, which was crazy frustrating. Otherwise, I would have a nice collapse movie to you, to show you. But then we did it another way. This is Matthias. He designed Rhino Vault. So he typically programs, I'm saying. He's,
Keep going.
All right, actually, it's really good. I recommend that you tear down everything at least once. You really learn a lot. In the beginning, we thought that maybe this might do something, but remember the images in the beginning? We have so much force flow. Oh, yeah. Okay. So again, we don't do this every day, so this is the best documented shell destruction ever. Now you have, of course, a little bit of bending capacity, but not for long. You see that it cracks where it wants to crack. And then Marcel, he's a professional drummer, so he knows how to hit, how to use a hammer. So you will see that already that it's not a problem of stress, it's a problem of good geometry, right? Good. So it's still standing. So what's going on? So you see the benefit of good double curvature, right? It gives you a lot of resilience even after you basically, okay, so here then Matthias did a nice project to seaplane. But after this, we noticed is that we used a lot of material to describe the geometry, which is, compared to the traditional tile vaulting, very wasteful. So in follow-up workshops, we try to address this. Can we find a mix between the efficiencies of tile vaulting and nonetheless describe a more complex geometry? So in this workshop with Tim Shork and Grimshaw in Melbourne, we did this little vault. Perhaps it doesn't look that spectacular, but what's special about it is that all the ribs in plan are perfectly straight. So this is again something extremely easy to be done with Rhino Vault. I challenge you to do it very quickly in Kangaroo. But why do we do this? Is basically because then you can describe the ribs very efficiently, very cheaply, and in between you can use traditional tile vaulting. So this is our attempt to not funky geometry, but to try to go back why we started using tile vaulting in the first place, right? That it's a very efficient way to cover space. And this then became a quite convincing demonstrator. I had to leave a little bit early for this workshop, so I missed the party. And even though we designed this booth, but now what's exciting, and actually, David, you don't know this yet because you worked on this, but they just bought the land, so this will actually be built. There will be an acoustically optimized big auditorium in Colombia, in Barranquilla, that will be built with this system. So the geometry is very specific because it's acoustically optimized, but it will be built locally. Okay, maybe more exciting are these kind of structures. This is just pieces, stereotomic kind of pieces, 3D printed without any glue, held together just by compression. This was one of the first models, just 40 centimeters, but I still like it. It's one of my favorite models. And we designed it in a specific way that are attracted in the back, and you'll see why that is important. So here you see the black outfit. This is Matthias the Destroyer again. He's basically demonstrating that we are not cheating. So this is really an equilibrium shape. It's really standing like this. This is a model from 2010, by the way, but it's still, I like it because it's very clear. And it was one of our earlier kind of eureka moments. Actually, that because of the thickness of the shell, you have multiple load paths. And here you see what happens. We attract force in the back. So this is actually a good thing from a structural standpoint, that local collapse doesn't propagate in global collapse. So in this case, what's good is that we kill only half of the people and the rest can get out by the time that the rest collapses. Anyway, this is a bit of a joke, but also a big challenge. How can you design these structures that are so kind of without much the typical redundancy that we get in order that they collapse in specific ways? And that is one of the very hard research topics. But these beautiful structures, this is Westminster Abbey, How they're being cut up is not just an aesthetic property. It also has to do with the flow of forces. It also has to do with how these stones were fabricated. So for this new type of geometries, we actually, so for example, developed with RhinoVault, we had to develop some algorithms that, for example, make all the interfaces, how is that going to work now, as perpendicular as possible to the force flow so that you don't have natural sliding in between the faces. So these are important things that you need to consider. How can you build this efficiently? So there is very hard geometrical constraints that you need to impose. We're still working on, and we don't know when this is going to come out, is for a big park in Austin, Texas, where we wanted to have these beautiful shells of Heinz Isler with these open edges that welcome the public. But this was done in reinforced concrete. These beautiful tensile structures by Fraiotto, where you basically, these are tensile structures. This is the masonry shells. So this was a project, again, that started in 2010 with main spans of 35 meters here, where we tried to really bring all these techniques, but then in unreinforced masonry. So there the result had to go to an exhibition. So we wanted to have a beautiful structural model. Again, don't forget that this is a real structure at a certain scale. And because of the stresses being so low, we can basically scale it up to a larger structure. So here, very careful decentering. This was a very painful puzzle of 870 pieces, but there it was standing as a structure. Because it had to go to an exhibition, we didn't want the first visitor to make it collapse, so we did this little move client. So again, this is Matthias in black, applying a load equivalent to Godzilla jumping on one leg on the X of your shell. To happen, what you see, by the way, is a lot of deformation, right? So these compression structures have a lot of capacity to deform. So in the case that Godzilla might come back, then this beautiful collapse would happen. And you see several issues. One thing is the client asked, can you not add that part to the movie that I will show to the city of Austin? They might not be as excited about this part. And the other thing that you see is that we killed everyone at the same time. So there we have done a lot of research to understand these methods, and we improved since then. This project, and mentioned it, is that we recently realized this kind of structures at a much bigger scale. 4 years ago, we were invited by Zaadit, by Patrick, to be part of the reference part of their shell exhibition. And there, basically, this little shell was standing in exactly the same room where we built now our shell 4 years later, 18 times bigger. So this was a kind of a neat coincidence. So there it was standing until very recently. The biggest success we had with our collaborators in Texas was the most sensational doghouse in the world. This is a cut stone doghouse. Anyway, it's not that important, except for we won the prestigious Barchitecture 2012, so, which is actually true. So now let's go to the, so the Venice shell, many people involved, but more specifically, my group did the architectural and structural design and the architectural geometry, meaning the fabrication optimization. My office, the old dirty bastards, did the structural engineering. And then our long-term partners in Texas, the Escobedo group, did this amazing fabrication. And because this is typically a question, why did I do this in Texas? Why not doing this in Italy? All the machines come from Italy, all the stone is in Italy. Why did I do this with partners in Texas? And that is actually maybe a very important point to make before you even see what I show you, is that if you push the limits, send digital files and expect that everything goes perfect. You need a lot of understanding of the processes, of the crafts. You need a lot of trust, and you need years of experience of understanding each other's capabilities, limits, and opportunities to really do exceptional things. So that is why I did this with my partners in Texas. What are we talking about? So as I said, we scaled this up. This was until Sunday, so until 2 days ago. In the Biennale, we have main spans of 16 meters. These are 399 cut stone pieces without any mortar, any glue, any reinforcements, just geometry keeping it together with just 5 centimeters in the middle. And I'll come back to this later. One of the big challenges is that the Arsenale is a historic protected site. So we had to be very careful how we basically put these 24 tons of stone on the inside of the structure. So we needed supports that equally distribute the stresses, but then also because we couldn't anchor, remember you can only activate compression when you control the boundary conditions, we had this system of tension ties that equilibrate